2.3, Part 1. We're going to look at long division of polynomials. If you're told a polynomial has a 0, specifically, and for this example, x is 2, then you know the factor was x minus 2. So if we know a factor, we can use long division to find the rest of the polynomial. This is just another way to be able to factor things down, to be able to solve things, is to divide out a factor to get what's left over. When we are doing longhand division, we always set things up in order with every position, meaning exponent, accounted for, meaning this is the cubed, this is the square, this is the single, and this is the constant. So if for some reason it went from cubed to a single, I would have to account for the squared position by putting in a 0. We always have to make sure every position is accounted for. Then when we start dividing, the only thing we look at is the first term of the divisor that's on the outside. So the only thing we care about is the x. The minus 2 is like a tag along. And as we go through our problem, the only thing we care about is the first thing that we come across. Okay, so in this case, all I'm looking at is the x and the 6x minus 3. And I ask myself, how is 6x cubed divided by x? So if you need to write that out separately, feel free, but you should go, oh, okay, well, x goes into 6x cubed, 6x squared times. All right, if you were to reduce that out, you'd get 6x squared. That's how many times it goes in. Now with long division, just like back in grade school, when we know what we go into, then we have to multiply around. And that's exactly what we're going to do. But we do have to use the tag-alongs. So it's 6x squared times x, but it's also 6x squared times the negative 2. So negative 12x squared. And I line up my positions. So if this would have multiplied to a single x, then I would have put it over here under the single x. But it multiplied to a square, and it multiplied to a cube, so I line up my cubed and my squared positions. Now again, just like back in grade school, when we multiplied around, we then subtracted. And when I subtract, I got to make sure to subtract all pieces, which means switch signs. When we do this, the first one will go away. It has to go away. If it doesn't go away, you did something wrong. You have to get rid of that first term. Then I combine here, so I get negative 7x squared. The rest of it comes down just like you did in elementary with a normal longhand division problem. Now we start again, but this time we look at x and negative 7x squared. So negative 7x squared and x, what does that reduce to, or how many x's go into negative 7x squared? You should be able to reduce that to negative 7x. Now we're going to multiply it around, and when I multiply it around, negative 7x, I get negative 7x squared. Negative 7x and negative 2 is positive 14x. Switch my signs, because when I subtract everything, and subtracting means switch signs. First one goes away. It has to go away, or you did something wrong. So 16 minus 14 is 2x. And we do it again. How many x's go into 2x? We get 2. Multiply around. 2x minus 4. When I subtract, I switch signs, and I have no remainder. this was a factor, because we told it to you. If something is a factor, it goes in evenly, no remainder. Same thing happens with polynomials. If it's a factor, it will divide in evenly with no remainders. So x minus 2 is a factor. 6x squared minus 7x plus 2 is another factor. If you wanted to verify it, x minus 2 and then the quotient that we got, if you distributed all of this combined like terms, you're going to get that, because that's what it means to divide in evenly, is that these two things multiply together to be that dividend. Okay, so here we have a polynomial, and it's divided by x plus 1. So there's my factor x plus 1. There's my all of my terms, x squared, 3x, 5. Every position is accounted for, a squared, a single, and a constant. So I start with just looking at the x and the x squared. How many x's go into x squared? X. When I multiply around, I get x squared plus x. Switch my signs because I'm subtracting. First one goes away, always has to go away or you did something wrong. And we get 2x plus 5. X into 2x. So again, we're only looking at the first term, and we get 2. Multiply around, 2x plus 2. Subtract our signs means switch our signs. First one goes away, it has to, and we get 3. Now I look at x into 3. Can't happen. Doesn't work. There's no way I can divide x into the 3. So this is now my remainder. And just like elementary, what do you do with remainders? You put them over the divisor. And we always put this little plus sign there. Alright. Page 2. If f of x and d of x are polynomials, as long as d of x is not 0 and the degree is larger, greater than or equal to f of x, there is a unique polynomial, meaning you can divide it evenly. Alright, so what does all that mean? Let's just jump down here. X cubed minus 1 divided by x minus 1. So there's our divisor, x minus 1. Well, I didn't have a square term, so I had to put it in. I didn't have a single term, so I had to put it in. And then the minus 1. This is what it means by fill in the positions. Everything needs to be there. And again, we start with, so let me just kind of highlight that. Make sure you fill in all positions. Alright, start with the x and the x cubed. X goes into x cubed, x squared times. Multiply around, we get x cubed minus x squared. Subtract means switch your signs. First one goes away and bring everything else down. Alright, x squared divided by x, so we get x. Multiply around. Switch our signs. First one goes away. We get x minus 1. How many x's go into x? 1. Multiply around. Switch our signs. We get a remainder of 0. So again, x minus 1 is a factor, and so is x squared plus x plus 1. Alright, this longhand division is just that, longhand. So we do have a shortcutted division. It's called synthetic division. And it only works when our divisors are of the single x variety, not x squared. We don't do that. It has to be x and then some number. So what the pattern is we line up. These are all the coefficients, C, A, B, C, D. Those are all the coefficients. And this is our 0. This is our factor, our 0. Notice it's a solved factor. So if this says -3, then we put +3. If it would have been +4, we would have put -4. It's our 0. The way that synthetic division works is that we bring down and then we multiply around. And then we add down and multiply around. We're going to add down, multiply around, we're going to add down, and that's going to be our end. Now this is always your remainder. I always have you put a little dash there, so that way you know that it's a remainder. So you're going to want to add in that little dash, and it will separate out the polynomial from the remainder. So the vertical pattern, the up and down pattern, is adding. The diagonal pattern is the multiplying by k. And we're going to practice this. So, okay. All right. So first of all, we make sure we have all the coefficients. This is what we're dividing by. So the divisor is -3. It's always opposite of your factor. So here's our -3. Okay. And we have all of our coefficients, 1, 0, because every position has to be accounted for, 10, 2, and 4. All positions accounted for. So there's no cubed, then a 0 goes in its location. Now we know the last location is our remainder, so I'm going to put that line or the dash or whatever. But I really want to make sure I understand that that's going to be a remainder. Alright, so the way it works, the first one comes down. Then we're going to multiply around. -3 times 1, -3. Add down. 0, -3 is -3. Multiply around. -3, -3 is +9. Add down. -1. Multiply around. -3, -1 is +3. Add down. +1. -3 to 1 is -3. Add down is a 1. Alright, this is your remainder, and everything else goes in order. So this is your constant, your single x, your squared x, your cubed x, to write it as the final answer. The other way also is that your first answer is always 1 less than your original problem. If it started off at the 4th power, your answer is going to start off at the 3rd power. But I tend to always work backwards. If this is my remainder, this is my constant, single x, squared x, cubed x, and they keep going in order. So if I was going to write this as a final answer, I would say 1x cubed, so just x cubed, minus 3x squared, minus x plus 1 plus my remainder, and my remainder is always 1 over my divisor, or it's my remainder over the divisor. Okay, let's try it again. here's our divisor, x minus 2. So opposite, positive 2. So positive 2 is what's going on the outside. Now everything inside is coefficients, and I need every position accounted for. So there's the fourth position, third coefficient. There is no second, so I need to put a 0 in. First, and constant, knowing that my last one is my remainder. Okay, bring it down, multiply around, add down, multiply around, add down, multiply around, add down, multiply around, add down. Remainder, constant, single, square, cubed, or it's always starting one less than my original. So my solution to this is 2x cubed, 3x squared, 6x plus 9, plus my remainder over my divisor of x minus 2. Alright, the remainder theorem, if a polynomial is divided by some factor and you get a remainder, it means that when you divide by that factor, that's actually your value. And what that means is f, in this case x minus 3, would be f of 3. So use the remainder theorem to evaluate the following function, x equals negative 2. In other words, find f is negative 2. All this is really doing is you're finding the coordinate point on the graph. Whatever the remainder is going to match up to the coordinate of this. So with this remainder theorem, what it's actually finding is the coordinate y point to the given x point. Right? So in this example, I'm finding f of negative 2. So in this case, x is negative 2. That's my divisor, negative 2. Negative 2. Every coefficient position, every position accounted for. So 3, 8, 5, negative 7. The last one is the remainder. This remainder is going to be the y coordinate point of x negative 2. That's what the remainder says. So just kind of to quickly go back up here, if I wanted to know on this graph, the graph of this polynomial, what the y value of 2 is, it's 19. All that does is tell me if I were to graph this at 2, somewhere up here at 19 is the point on the picture. Alright, so here, when we do this synthetic division, bring down, multiply around, bring down, multiply around, bring down, multiply around, bring down. So f, and that should say negative 2, f of negative 2 is negative 9. On my picture, this point exists. When I graph this line, this point is on it. That's all the remainder theorem tells us. Factor theorem. What the factor theorem is, it's kind of the same thing as the remainder theorem, but what happens if I get a remainder of 0, whatever I put in here and I get 0, all that does is it tells me it's a factor. So it just tells me it's a 0, it's an x-intercept, it's a root. So in this case, negative 2 and 3 are factors. I'm going to start with the first one, and here's my polynomial, So I'm going to go 2. Put in all of my coefficients and do my synthetic division. So bring down, multiply around, bring down, multiply around, multiply around to 18, I get 36, bring down is 9, 18, last position is the remainder of 0. Okay, I proved that it is a factor, I proved it is a root, I proved that it is a 0, and it means that on my picture at 2, it's going to cross the x-axis. So x minus 2 is a factor. Let's see, this is going to be 2x cubed, 11x squared, 18x plus 9. Now, if you know you have more than one factor, and we do, because it said we had minus 2 and we have the x plus 3, then I can keep going. So I'm going to use my negative 3, but I'm not going to go back to my original. I knew x minus 2 went in, so that part's out. So I'm going to just do the leftovers, every position, every coefficient. The last one's going to give me the remainder. Bring down, multiply around, bring down, multiply around, bring down, multiply around, bring down, 0, it's a factor. So I know x minus 2 is a factor. I know x plus 3 is a factor. And leftover, 2x squared plus 5x plus 3. What's good about this, especially if you already know 2 factors, is you can very quickly pull down into something that, as it stands, you really wouldn't be able to factor this or solve this without graphing it. But by knowing a factor, I can break it down to an easier polynomial. Again, I could try to factor this, but not too easily would that happen, so I can divide out another factor. Now, this leftover piece is very easy for me to be able to factor into my 2 pieces. So I can find all 4 of my factors, which means I can find all 4 of my zeros, and I know there's 4 of them because that's what my n is, my exponent, just by doing this synthetic division to get smaller and smaller polynomials to factor. So just to kind of sum it up, and you can read through it, but the remainder does tell us a lot of the picture. It can tell us if it's a factor, it can tell us a point on the graph, it can tell us the remaining factors. So there are a lot of good things that the remainder factor and the factor theorem can show us. And that's part 1 of 2.3.